Our story begins in 1966, the year an unmanned spacecraft lands on the moon and beams back this, the very first image of the lunar surface to Earth. That same year, we have what in the AI community is probably the most notorious example of AI hype. In fact, it's the first. Two researchers at MIT, now world famous, proposed a project in which a couple of students, over the course of a summer, would solve a large part of the AI puzzle. They would get object recognition in images. Needless to say, they didn't exactly succeed, and people realized this was going to be just a little bit harder than they had first imagined. This is a story which has been repeated year after year from that day until this. As has been mentioned, I've been at Nearmap for almost 2.5 years and have accumulated a team that's rapidly approaching 20 people. And let me just tell you a little bit about them. More than half of them have PhDs. There's a bunch of university medalists. I'm not sure if that's the appropriate collective noun, but we'll go with a bunch. And they're just an unreasonably talented group of people. And they've been working with complete focus and dedication on just one project in that time. Today I get to share that with you, and believe me, it's been a long time coming. But first, indulge me, I'll give you a little history lesson to give you some context and ground you. So let's move on from this, the birthplace of AI, and we'll give them more than a summer. We'll go 15 years ahead and check in. In the interim, humans have landed on the moon. The entire Apollo space program has run its course, and a new thing has been invented. The space shuttle takes its first flight in 1981. What about AI? Well, we can take an image like this. We can make it black and white. We can hunt for some triangles and rectangles, and then that text on the right is basically a handwritten recipe describing the exact configuration of triangles and rectangles that you're hoping to see in a Boeing 747. You can see what they're trying to do, but it doesn't take much imagination to realize that if you tilt the plane in the image just so, the recipe breaks and all bets are off. At this point, there is no practical application of AI. So let's go further, let's go faster, 45 years beyond that initial project. The year is 2011. Remember that space shuttle? They take their final flight this year. The 30-year program ends. Constellations of satellites are whizzing around the globe, communicating with the iPhone 4 in your hand, enabling an amazing new feature, the ability to geotag a photo of your cat. Cats turn out to be a really good segue to AI at this point, because we've just figured out how to detect them in an image with a reasonable degree of reliability. Unfortunately, though, it's still very much a manual handcrafted process. It looks more impressive than the text recipe, but you're still crafting these algorithmic steps, fiddling and tuning for your problem, and just hoping it works. In terms of industry applications, we actually have some. Out there on factory floors and assembly lines where lighting is well controlled, you know the objects ahead of time, and there's no surprises going on. The messy real world is left as a problem for another day. What if we just go one more year? Let's meet some researchers at the University of Stanford. They believed that the big breakthrough was not going to come from better algorithms, nor was it going to come from more computing power. The vital missing ingredient was data. So they assembled a data set of 1.2 million images and somehow convinced human volunteers to hand label every single one of those images with one of 1,000 categories, from water buffalo to Savoy cabbage. They then started an annual competition. Nothing much happened in the first 2 years, but in the third year, University of Toronto researchers hit the jackpot. They were trying out a new technique which got coined as deep learning. The error rate halved overnight. Year after year, records fell as Google, Oxford, Microsoft jump on board with this new technique and refine it. The competition ends in 2016. Why does it end? Well, remember in 2011, the previous slide, we were doing well to recognize a cat in an image. In 2016, just 5 years later, We can detect which breed of cat is present in the image with better than human accuracy. They could no longer measure who was the best in the competition because the benchmark, the gold standard, was too flawed. Naturally, this turned the world of research absolutely on its head, and things leaked over into industry. We have the giants like Google and Facebook building software systems that take deep learning, this new technique, out of the hands of literally a few dozen researchers worldwide to every data scientist on the planet. NVIDIA and Google then battle it out for deep learning hardware. These are chips custom designed to do nothing but run these algorithms. Today, it's a $3 billion a year industry worldwide. In 10 years' time, it's projected to be a $30 billion a year industry just for the hardware. A lot of that demand is being driven by the big cloud providers. The problem with these chips is they're really expensive, so the cloud providers buy them up in bulk and then rent them out to you at an hourly rate so that anyone can have a go. And in fact, that seems to be the message at this point, that we've got better than human accuracy on some problems, we've got all this software and hardware, anyone can have a go at AI. And I would guess that many of the companies represented in this room, there's someone who was hiding in the corner of your company, maybe a student, maybe a grad, maybe a keen employee, who's had a dabble with AI for a couple of months. And I'd also bet that they've probably come up with a pretty compelling demo, a prototype, because these tools make that very possible. In fact, I did the same thing when I started at Nearmap. I spent the first 2 months of my time there by myself just building a swimming pool detector. And it worked really well. In fact, I benchmarked it against a commercially available data set at the time, and my model had better results. In fairness, they were using satellite imagery and I was using aerial, but you use what you can get, right? There's a little bit more to it than that, though, right? You can't just do a prototype and you're finished. What we're seeing in the AI industry is an endless sea of exciting, successful demos and prototypes. What is rare as hen's teeth are the companies that are converting that to full-scale production products and systems. I wonder why. I think there's 3 main factors that drive a company to either succeed or fail in AI, and I'll go through them now. The first one is data, of course. This whole revolution, yeah, sure, it's about deep learning, but it began because of a data set. And it's as much about the richness, the nuance, and the accuracy of it as it is about the scale. There's a quote that says, "He who has the best data wins" in the AI game. When I was first kind of scoping out Nearmap and deciding whether to take the job, I saw just such a data set. Millions of square kilometers, high res, 10+ year history, top-down, multi-angle, 3D, the works. When you're going into the competitive world of AI, this is the data set you want at your back. What about software? I think of a machine learning model, and we'll get into the machine learning versus AI discussion later, but a machine learning model is a little bit like a brain. And just like a brain needs a body in order to do something useful, a machine learning model needs what I call an AI system wrapped around it. And that system is built of databases and data pipelines, people, processes, statistics, APIs, and systems. And instead of being built out of cells, these things are built out of software. So I'll go out on a limb and say that until a company has a mature software engineering capability, it is not yet ready to embark on the AI journey. Again, looking back at Nearmap when I first started, these guys are serving up billions of image tiles to customers all over the world and building sophisticated tools like the ones you've seen today. These guys, I thought, have top-notch software engineering. They've got their house in order, an ideal foundation for an AI system. Lastly, let's look at technology development, what people call deep tech at Nearmap. Building complex systems is hard. It takes time, design, collaboration, acceptance of risk, and above all, the ability to fail, pick yourself up, and go again. In my personal experience, the companies that understand this the best are the ones that build physical technology. Let me show you what I mean. I spent the first part of my career actually at the company Rob mentioned, Cochlear, where the goal is to take noisy, messy sound from the environment, digitize it, clean it up, turn that into precise electrical stimulations on nerves in the brain so that the deaf can hear again. It's a little bit complicated, and it's kind of miraculous that it works. I also spent a few years in underwater robotics. The game here is that you take a really expensive bit of kit like this, you program it up, and then you chuck it off the back of the boat in the deep ocean. Its job is to sink to the sea floor, perhaps 3,000 meters below, build a map, and then return to the surface exactly where you left it. Although radio waves don't work underwater, so you've got no GPS and you can't talk to it. The thing that these two examples have in common for me is not just that they're complex systems, but no amount of design, no amount of bench testing, and no amount of planning can prepare you for the spectacular and unexpected ways these things fail when they get into the real world. I know there's a bunch of people here in construction, and I think you get this concept. You spec out a design for a building like this, and you say there needs to be a column here. Okay, the load is going to be this much. What's your safety margin? Do you add 5%, 10%, or is it more like 5 times? Because of that real-world effect, the unknown that might occur. The relevance to AI systems is this. Data is the medium that carries this mess and this chaos into the neat and orderly confines of a software system. Lastly, bring it back to Nearmap. This was a company, I thought, that has been perfecting aerial imagery systems for over a decade. Cameras that can fly higher and faster than anyone else, doing battle with wind, vibration, and temperature. These guys, I thought, will have the grit and the tenacity to build a real working AI system. So, I signed up, became a Nearmapper, the team grew, and we got to work. Let's take a look. This is a screenshot from a freely available popular mapping platform. And this is the image that goes with it. I want you to notice 3 things. 1, the image is grainy and horrible. 2, there's no date stamp, you don't know when it's from. And 3, if we jump back a little, look at number 47. Look at that building outline, and then look at the image. Does that look anything like it? Not only do we not know when it's from, but there's at least 2 whens involved, and they're out of sync. Okay, let's get to some Nearmap imagery. Clear, crisp, current. There's a familiar date stamp in the corner. We've solved 2 of those 3 problems already. That's our product, that's it. Or is it? This is a machine learning technique called semantic segmentation. Skipping the technical mumbo-jumbo, what it allows you to do is paint pixels with meaning. Orange for roofs, green for trees, blue for swimming pools, yellow for solar panels. The list can go on. I only want you to note one thing about this image, and that is that there's no Photoshop, there's no manual touch-up, there's no hiding the dodgy corners. This and every other image and bit of data in my presentation are automated, real, straight-up output from an AI system. Okay, let's draw some rings around the key objects, and we'll wash the paint away so we can see more clearly. First, let's have a look at that swimming pool in the mid-left. Can you see it? I wonder if you would have picked that it's there if the algorithm hadn't highlighted it. It is visible to the human eye, but you've got to pay close attention because it's in such deep shadow. What about the roofs on the right? We've got shadows from trees, and then look at the bits where the trees actually physically overhang the roof. What your brain does when you look at that image is you say, well, I know what roofs look like. I'm going to extend a line out there through the tree because I know there'll be roof there. The majority of the time, the algorithm does that too. It's basically magic. I hope you'll agree this is starting to get interesting at this point. And just as an aside, I wonder how many of you have a map browser project that looks a bit like this, except I guess you had to draw all the shapes yourself. All right, let's get some property boundaries and overlay them over the top. You can get these for free or a fee in any country around the world. You can then associate all of these objects with that correct property boundary. And you can turn that into a spreadsheet. Each row as an address, each column as a fact about that address. Does it have a swimming pool? Yes or no. Does it have a solar panel? Yes or no. I would hazard a guess that every single person in this room is capable of loading and doing something with that data set. In fact, I'm willing to bet my career that enough of you can load it and do something useful with that data set that will benefit your business. Now, it's fair to say we're not the only company to have built a property attribute data set. There's others. So what's the difference? Well, all of the ones that I've seen out there suffer from the same weaknesses that I highlighted earlier. Largely speaking, they're built off satellite imagery, and the algorithms are magic, but they're not that magic. They suffer. Secondly, these data sets are typically built at some unknown when, years before, and not really kept up to date. So let's have a look at what happens just in the course of less than 1 year. If we have a static data set, what happens to that number 47? From Nearmap's perspective. House gets demolished, foundations go in. Walls go up. Roof trusses appear. The building's completed with solar panels on top, and then if you look at the back garden, there's an extra shed or granny flat or something going in. And this is what happens. Reality gets out of sync with the static data set. But hang on, these are our images, and our outputs are fully automated. There's no manual touch-ups, so why not just pass the fresh images through and update it? We go from static data sets to living ones that change and evolve over time as the city changes and evolves. But I think we can do better again. You guys are always talking about how you like our recent imagery, and there's only one possible reason for that. The world is a changing place. If the world wasn't changing, then the old imagery would be good enough, right? So let's talk about change. Let's go back to that spreadsheet I mentioned earlier, but we'll only look at one address. And we'll look at it on 2 different dates. We'll call these dates before and after. Let's look at solar panels. Before says no. After says yes. Congratulations, you have just detected the installation of a new solar array in a window of perhaps a couple of months. It's actually really useful. We call this simple change. But, and this is where it starts to sound like an infomercial, but there's no smoke and mirrors, there's more. So we can do complex change detection. Rather than just looking at the yeses and nos on a property, I don't want to spill the beans on exactly how we do it, because there's lots of little clever tricks, but essentially what happens is we take these objects and we compare them over time. We carefully ignore the many changes that you don't care about and highlight the ones that you do. Meaningful, intelligent detection of change over time. You want to know if that solar array has increased in size? We can do it. You want to know if there's an extra granny flat or an extra deck out the back? The algorithm can do it. Now, hope you'll agree that's a pretty cool demo. And that's where all the AI talks I've ever seen end, with a pretty cool demo and a long, distant view to what might be possible in the distant future, hopefully. But we've got 10 minutes left, so let's keep going. Who wants to zoom out? Oh, I almost forgot. We can put the trees back, and why not splash some construction paint on to show that there's still work going on in the property. Okay, that is 300 square kilometres of Perth. If you zoom into the correct spot of that image, you'll see that number 47 that I showed you earlier. If you do the maths, that works out to be a 10 gigapixel image. Let's add AI. That's what 10 gigapixels of roof paint looks like. Again, you can zoom right in and see what we saw on the previous slides. And of course, we don't just paint pixels with meaning. We find the objects, we summarize information about properties, and we calculated change over time. Let's have a change of scene while I explain further. This one's trees. I wonder if there's anyone here looking at heat islands or forestry or that kind of thing. Anyway, the really cool thing about this image is it only represents a tiny, tiny portion of what we've actually processed. Earlier this year, we embarked on a project, a somewhat ambitious one. We decided to push our entire Australia and US footprint through our AI system. Most recent date, and some old stuff too. That's 1 million square kilometres of full resolution imagery, 80 million properties, and approximately 3,000 times the amount of data you see represented here. And how long did it take? 3 weeks. This next one, I'm going to give you a new slide. Think about this. This is trees. We're going to look at a different plant Is a different plant going to make the city look different? We're going to look at grass. That's the backyards, that's the council strips, that's the sports fields. You can even see the golf courses with the kind of snake-like pattern. I wonder if anyone's doing impervious surface modelling or runoff. Anyway, I digress. I was talking about that project and the scale of it, doing it in 3 weeks. Let me try and give you a sense of it. We spoke to Amazon, who is the world's largest provider of cloud computing. These guys really know what they're doing. But when we explained the ambition of our project, their eyes widened a little and kind of they said, "Are you sure you want to do that?" And it became clear throughout the course of the project that we had entered a new game where we were pushing systems further than either most or any of their customers had before. We'd graduated from the sandpit and were playing with the big kids. Just to give you some numbers, we had to run in 18 data centers for that 3 weeks just to get enough hardware to run this thing. Not bad for a little Aussie tech company, hey? I think it's fair to say we're punching above our weight. All right, next up, construction. Everything from the little hobby project, adding an extension, repairing a roof, all the way through to the big infrastructure projects that are shaping our cities forever. And what construction reminds us of is that the world is a changing place. Now, you might think it's kind of silly to set a challenge of 3 weeks to push our entire footprint through our system, but there's a reason. That was done on data from January. That stuff's old now. Have you seen how much changes in a city in the course of 6 months? So we're already running, as we speak, an update to our data set before it's released, just to keep it in sync with reality. In fact, we've got a commitment that from this point forward and onwards, every single survey we capture, we will produce AI output. AI pixels glued to every visual pixel. What's more, the model we're currently running, it doesn't just have the handful of categories you see here, swimming pools, solar panels, etc. We've gone from a handful to 30 or more categories. And we're still growing. All right, let's look at the last layer. This one's a little harder to see, so kind of tune out a bit, pretend you're looking at the Milky Way and let your eyes focus. The faint pinpricks of light are the residential solar installations. The larger bursts of colour are the commercial ones. It's a heartwarming picture for those who are into renewable energy. In fact, if you were to look at Perth over the 10-year history that we've captured and calculate the AI layer on all 90 surveys, which we did, you can just build a bar graph. Solar uptake from 2009 through to 2019 goes from about 1% to more than 20% in those 10 years. And those numbers are based purely on our imagery, nothing else. All right, I'm getting distracted again. I was talking about going from those handful of categories to 30 or more. How do you do that? Because most people, when they're doing machine learning, they build a data set, and then they build a model, and then they're done. We've done something quite different. We've built an engine that can create data sets, plural. We've built an engine that can create models, plural. So if you want to define a new attribute, let's say tiled roofs, you need the ability to, first up, define it, come up with a sensible definition. Then you need the ability to get that labeled by humans on probably something like 500,000 images of properties. That's no small task. Then you need to take that large data set, wind it through and retrain your models. Again, not too easy. And then you need to be able to push out an update to your full footprint to make that new attribute available to your customer base in a timely fashion. On all counts, we have that ability. So please, bring us your requests. One more. We're going to take all those layers and we're going to glue them together into one glorious semantic view of Perth. No visual pixels, just pixels of meaning. And I want to talk to you about accuracy, because everyone wants to talk about accuracy. But I don't want to give you numbers or kind of bamboozle you with technical waffling. I'm going to give you an anecdote which will help you in a much more practical way understand how accurate these models are. We have a routine process. The models are so good that we've got this just baked-in routine process where every time a human labels an image, we get the machine learning model to label the image as well. The vast majority of the time they agree, because they're both really good at their jobs. But what happens when they disagree? We send that image back for checking. Let's just check if there's something going on here. And it turns out that more than half the time, the human says, oops, machine got it right. The implications of this are profound. If you have expert humans doing a repetitive task that they are well trained to do, these models are more accurate, more repeatable, and can operate at far, far greater scale than you can imagine. And now we get to that so what moment. Why build this in the first place? Is it just because of those industry conditions I mentioned, that industry conditions are perfect? Is it just because Nearmap is the ideal foundation for an AI system with that really juicy data set? Well, it is, but there's more. You'd be forgiven up till this point for thinking that our mission as a company was to deliver beautiful imagery. It's not, although we do that. As Rob mentioned, our mission is to change the way you view the world so that you can profoundly change the way you work. We believe there is an enormous gap between just delivering you imagery and what we can do with AI to help you achieve your goals more quickly, more efficiently, and at greater scale than you ever have before. I'm going to show you now a little bit of analysis I did. The data set's complete, just jumping on, having a play and see what it can do. This was literally a few evenings the other week. Let's look at every postcode in New South Wales, shall we? And let's pick the top solar by postcode. Where is it? Newington. It's an interesting pattern. If you look closer, you'll realise that is the Sydney Olympic Village, where every single house had a solar array. So they have 72% solar uptake in that postcode. What comes second? Terra Nora. I've never heard of it either. Sounds like something out of a sci-fi movie, but it has 48% solar uptake. So maybe it is. Actually, it's on the very, very, very north coast of New South Wales. And if you want to find the corner of New South Wales that has the most sunshine, it actually makes sense. Let's go further afield, because as I said, we've done the full Australian-US footprint. So I thought, why not have a poke at a US city and see what happens? Let's look at Houston. What do we reckon the solar uptake in Houston is? I'll give you a clue. It starts with a 1. It's 1. 1% solar uptake in the top zip code in Houston. That's the top zip code, not the average. Not only have they been slow picking up solar, but when they do, they put it all in the corner. This is policy right here. I spoke to a lady from the US after the Melbourne event, and she was saying, look, we really want to put solar in just like you guys, but costing's different, policy's different. So I had a look, and it turns out that these guys get absolutely not a single cent back when they feed in extra energy to the grid. Not a cent. So you can see policy right there on the screen. Imagine you're a solar installer, and you get this data. What do you do with it? You can look at the rate of new solar panels going to any suburb in the country. You can work out where the hotspots are of activity that you can jump in and try and go for installations as well. Or maybe you step back, think bigger, and say, well, I could calculate, if I combine this with my own data, I could calculate my market share of new installations going into any suburb. What if your solar responsibility is bigger at the state or national level? Wouldn't it be just great to have this national, consistent, reliably and regularly updated data set that was simply an accurate representation of the truth on the ground? Here it is. Up till this point, you've had to rely on either out-of-date satellite-based imagery sets or, worse, paper forms filled out by solar installers that you hope make it through and get updated. Those days are gone. Let's move on. I'm going to give you one more image with solar. This is just to show that the US does have residential solar. In New York, the top suburb, despite having far less sunshine, is Staten Island with 10%. Again, policy. But let's move on from the world of solar. Let's talk about construction. Let's go back to New South Wales and say, where's the top construction happening right now in New South Wales? I'm not in the construction industry, but what pops out right at the top is Marsden Park, Leppington, Box Hill, Gregory's Hill. Are these places familiar? All between 5 and 15% of properties undergoing construction work as of January 1st this year. If you're a local council and your job is to kind of know what is going on in your area and keep up with it, how do you do that? Even in hotspots like this, only maybe 10% of the properties are undergoing change at any one time. What if you could use our data to zoom in on the areas of your council that are changing so that you can either address them individually, maybe updating rates based on actually what's there, or maybe you step back and think bigger. Maybe you say, I can use this to work out whether we're building enough infrastructure to keep up with upcoming demand. We'll do one more. And we're going to go right back to the beginning where it all began, and we'll do swimming pools in Los Angeles. What do you reckon the top zip code in Los Angeles is with 66% swimming pool presence in properties? The zip code is 90210. Beverly Hills 90210 just comes in at the top of the list. I'm like, I've heard of that place. Should have seen that coming. I know there's a bunch of councils around Australia who have the unenviable task of building a data set of every single swimming pool in their council, and they have to keep it up to date. I don't know how you even begin to approach that task without this data set. So hopefully we have some good chats afterwards. I want to be crystal clear at this point. We have petabytes of AI output already produced. We have our full coverage across the Australia and US footprint already done. The quality of the results is unparalleled in industry. We are already expanding our attribute set and updating the results with fresh imagery as we speak. Today is the launch of our content beta program. What that means is that the data is ready. General availability will come later. No prizes for guessing. Someday there'll be a slick map browser experience where you can interact with this stuff. But for now, we decided that it was time to take the wraps off and let this breathe. We know about a lot of use cases from talking to you, but we want open discussion about what you want to do with this data. Well, it's been fantastic to finally unveil what we've been working on, give you a glimpse of the future, and a little bit of the backstory and why Nearmap is an ideal foundation for building AI. I've given you the steps that we can do. We can paint pixels with meaning, we can find objects, we can summarize information about properties, and we can calculate change over time. I hopefully have whet your appetite with some potential suggestions on what you can do with this data. But at this point, I want to step back and really think big. What this AI system effectively does is it allows you to map the evolution of entire cities as though they're living, breathing things at incredible scale with incredible nuance. Whether you're in town planning, government, building developments, or just putting in a garden shed, this is the data that will represent our cities as they really are today and allow you to discuss what they should look like. This is the data that will help you plan how to achieve that vision. This is the data that will help you to execute those plans, and this is the data that will allow you to track your progress on that vision of better, more livable cities. By adding a radical new way to view our world, I believe we can profoundly change the way we shape it. And at this point, I think words fail to fully grasp the opportunity, so I'll do what we Nearmappers do best. I'll stand aside and let the pictures speak for themselves.